So let's talk about bond polarity and dipole moments, right? We talked about bond polarity in the last chapter, and we said that bond polarity arises from the uneven distribution of electron density in an interatomic bond. So here we've got hydrogen and we've got fluorine. The electron is going to spend most of its time around fluorine and less time around the hydrogen. It can't completely form an ionic bond. It's got to spend a little bit of time over there, but it's going to most of its time over here. And what will happen is we've got a partial negative end and a partial positive end to this bond, right? And this introduces a dipole moment. So if we've got uneven sharing, we can have a polar covalent bond. Like we've got here, these guys are unevenly sharing those electrons. Okay. We're going to represent an arrow that is going to point towards the negative charge. So you can think of this as being like a little plus sign for our plus charge, partial positive. And the tail end indicates the positive center. Another way to do this is to map this out using a color or a heat map, where red is going to be our electron dense region and blue is going to be our electron poor region. Any diatomic molecule with polar bonds is going to have a dipole moment in that molecule. You've only got two atoms, it's linear, it's only got the two atoms to it. The whole thing is going to be determined by that one polar bond. This behavior is also exhibited, however, in polyatomic molecules. So few molecules possess polar bonds but lack a dipole moment. We do have a number of them that have polar bonds but are nonpolar. Carbon dioxide is a great example of that. It occurs when individual bond polarities are arranged in a manner that they're going to cancel each other out. Right, so we've got these things, kind of looks like an arrow. You know what else looks like an arrow? Is a vector. So you can treat these guys like vectors. Okay? So looking at our HF bond, we've got a partial positive and a partial negative end to it, and it's going to introduce a dipole moment. But what if you've got more than two atoms? Right? We will treat these guys like vectors, and we will add them. So here we've got water, which has a partial positive and a partial negative end for this bond, so it's a polar bond pointing in this direction. And over here we've got a partial positive and a partial negative end on this bond. And what we'll do is we will treat those as vectors, right? So I've got an X component and I've got a Y component from over here. And on this one, I can decompose this into an X component and a Y component. Well, if I add those two things up, on the X, I got a X going this way and an X going this way. They're going to cancel each other out. Right? If I look at the Y, I've got a Y and another Y. They do not cancel each other out. And so what will happen is that we will have a net dipole moment that goes up through this molecule. Now, if I look at my carbon dioxide, on the other hand, right, I've got no Y component. I've got an X component going this way, and then I look at this guy and I add it up, and it's got a X component going this way, and they cancel each other out. If we were in a real classroom, I would put some people in some wheelie chairs, and I would have you guys push each other around to kind of simulate this, but hopefully you can imagine this in your head and see how these things are going to start to cancel each other out and form nonpolar molecules, or not cancel each other out completely and form polar molecules. Right? There are lots and lots of polar molecules out there. Can we predict polarity? Of course we can. You're going to determine the geometry of the molecular ion using VSEPR. You're going to look at the bond dipoles. You're going to look at the positive and negative ends. So you're looking at your electronegativity table. You're going to determine if the bond dipoles cancel each other out or not. In other words, we're going to do some vector addition in 3 dimensions. Right? That is the mathematical way to do it. The other way is called the method of similar regions. So we're going to look at symmetry within the molecule. Or if you want to Sesame Street that, one of these things is not like the others, one of these things just isn't the same. If one of those things isn't the same, our molecule is going to be polar. Right? So we're going to consider tetrahedral methane, right? Ammonia and water. We've got 3 tetrahedral molecules. What's going to be polar, what's not? Right? So lone pairs are going to disturb our symmetric molecule, making it polar. Right? We can draw the vectors. It's not as easy to visualize in 3 dimensions for that. So what we can do is consider regions that are similar within that molecule. So looking at our electron arrangement for a linear molecule, we're going to look at the ends, right? So something that would be like HH, right? They're similar, it's going to be nonpolar. Something like HCl, those are different, it's going to be polar. Right? If I'm looking at something that is trigonal planar, I'm going to look at the 3 corners. So something like boron trifluoride, where all 3 are fluorines, right? That's going to be nonpolar. And something like H, right? Change one of those into an H, right? This guy's going to be polar. One of these 3 things is not like the others, it's polar. Right? A tetrahedron, we're looking at the 4 corners. So our methanol, methane, which has 4 identical carbons in it, that's going to be nonpolar. But something like water, where I've got carbon, oxygen, a lone pair of electrons, another lone pair of electrons, hydrogen, and then another hydrogen, right? Those aren't all the same. Right, so this guy's going to be polar. Right, our trigonal bipyramidal, we're going to treat the axis as one set, right, and then our hula hoop around the middle as another set. Right, so if we do something where we've got phosphorus, and instead of phosphorus pentachloride, we've got chloride, right, phosphorus pentachloride is going to be nonpolar. Right. Change one of these guys to a bromine, now it's polar. Right. So if we do an octahedron, right, same idea as the previous one, we're going to treat the axis as one set, and now we've got a square hula hoop around the middle. Right. We're going to look at the axis as one group, and then the guys on the equator as another. Yep. So how do we determine if it's polar or not? If the similar regions are completely occupied by identical entities, atoms, lone pairs, unpaired electrons, nonpolar. Right? If all similar regions are not occupied by identical entities, atoms, lone pairs, unpaired electrons, the species is going to be polar. Right? So here's an example where we've got sulfur hexafluoride, and it is nonpolar. And then you've changed one of these from a fluorine to an iodine. This molecule on the right is polar. Right, so it's not going to have completely canceling. All of these guys along here will completely cancel each other out, but fluorine is going to have a really big dipole moment. Right, iodine is going to have a big one going in this direction, but it's not going to be as big as fluorine, and so we'll end up with a net dipole that's going to go down through that molecule. So sulfur hexafluoride, fun stuff. So types of molecules with polar bonds, but no resulting dipole moment when they cancel each other out. Right? So if it's a linear molecule, the left and the right, the x components cancel each other out. Carbon dioxide is a great example of that. If you've got things that are in a trigonal pyramidal structure, all 3 of them will work together. If you decompose this vector into x and y components, the 2 y components here will equal the y component going up here. That's going to be completely polar or completely nonpolar. Same thing going on over here. It's just a little bit harder to visualize it. Right, so from our electronegativity values and their periodic trends, can we predict each of the following molecules is polar and show the direction of the bond dipoles and the overall molecular dipole when applicable? Right, so ammonia, NH3, boron trifluoride, carbonyl sulfide, which is going to have an atom sequence of SCO. All right, so our plan, we're going to draw the shape. All right, so we're going to Lewis structure, find the electronegativity values, and then combine those concepts to get the polarity. So looking at ammonia, right, there is our Lewis structure for ammonia. I've got hydrogens here and a lone pair. Right? Our method of similar regions would say, yeah, this thing is not the same as that. Hydrogen and lone pairs are not the same. If we look at our electronegativity difference, we're going to end up with 3 for nitrogen, 2.1 for hydrogen. It's a polar bond. Right, so we're going to end up with some dipoles, some bond dipoles. Right, and those bond dipoles are going to result in a molecular dipole. The dipoles reinforce each other, at least in this vertical direction that goes straight up through the molecule, and so the overall molecule is definitely polar. Right, and there it is as one of those thermal heat maps. Boron trifluoride has 24 valence electrons, and all electrons around the boron are going to be involved in bonds, so our shape is going to be AX3, or trigonal planar. The fluorine is going to have 4 as its electronegativity. Boron is 2, so all of the dipoles are going to be present. They're all going to have polar bonds, but they're all going to cancel each other out. They're at the same angle, the same magnitude. Our molecule is nonpolar. Notice how this is all even in terms of its electron distribution. COS is linear. The carbon and the sulfur are going to have the same electronegativity too, but the carbon-oxygen double bond is quite polar, and so overall that molecule is going to be polar. So we've got this molecule here, which has a polar bond between the carbon and the oxygen, and we've got no bond over here, or no polarity in this bond, so we have an overall polar molecule. Right, so let's predict the polarity of some of these molecules. So we've got HCl, Cl2, SO3, CH4, carbon tetrahedral with the carbon atom at the center, and H2S, which is going to be V-shaped with the sulfur atom at the point. Right, so looking at HCl, it is a linear molecule. It's got a polar bond. There is only one way you can arrange that. If it's a linear molecule like this, that's a linear diatomic with no lone pairs or anything on it, it is going to be a polar molecule. Right, so got a polarity difference. The bond, there is only one bond. Our molecule is polar. Our Cl2, I've got 2 chlorine atoms. They're going to share that electron density equally. There's no polarity difference between one chlorine and the other. It's a nonpolar bond. There's only one bond. It's a nonpolar molecule. Right. For our SO3 molecule, the electronegativity of oxygen is quite a bit greater than that of sulfur, which means that the oxygen is going to have a partial negative charge, and the sulfur will have a partial positive charge, so our individual bonds are polar, but because they are arranged symmetrically, they're going to cancel each other out. The molecule has no dipole moment. In methane, carbon is a little bit more electronegative than the hydrogen, so you're going to have slightly polar bonds between the carbon and the hydrogen. But again, their arrangement, because they're symmetrically opposed to each other, is going to result in cancellation of those polarities, and the molecule has no dipole moment. Our hydrogen disulfide molecule has polar bonds between the hydrogen and the sulfur. It's got some lone pair of electrons over here that they're not showing. But our sulfur is going to have a little bit of a negative charge, and our hydrogens will have a partial positive charge. While they will cancel each out in the x dimension, they do not cancel each out in the y dimension, and so you end up with a net dipole that goes through the molecule like that. Right? In more complex molecules, and so we've got 2 different molecules here. One is cis-2-dichloroethane. Right? So we've got similar regions in cis-2-chlorodiethane. We've got 2 on the same side. Right? And then here in trans-1,2-dichloroethene, we've got similar regions where the chlorines are on opposite sides of this dashed line. And so my bond between the chlorine and the carbon is going to cancel out with this chlorine and this carbon. And this hydrogen carbon bond and this hydrogen carbon bond kind of cancel each other out. If I put them both on the same side, however, right, they may cancel each out in the x dimension, the chlorine carbon and the chlorine carbon, but not in the y dimension. The same thing with the hydrogen. So this molecule is going to be polar, and this molecule is going to be nonpolar. A little bit of history, since we are in Pride Month right now. The word cis and trans, the word trans for somebody who is trans comes from transgender, and the term cis, like cishet for somebody who is not, was an adoption of the chemistry term, which is kind of the opposite of being trans. So dichloroethane exists as 3 isomers. We can have it as cis 1,2, trans 1,2, or 1,1 dichloroethane. It just tells us where these chlorines are. So we said this one is going to be polar. Right? The bonds are going to be looking like this. Right? So they'll cancel each other. The hydrogens, polar bonds will cancel each other out in X but not in Y. And the chlorines will cancel each other out in X but not in Y. So this guy will be polar. In the trans 1,2 dichloroethene, we're going to end up with the bonds canceling each other out in both X and Y for chlorine and X and Y for hydrogen. That molecule will be nonpolar. And then our 1,1 dichloroethene, right, they're not going to cancel out in X. They're not going to cancel out in X, even though they will cancel out in Y. That molecule is going to be polar, right, with a net dipole that's going kind of through those 2 carbons as opposed to across it. Right? You'll notice that these are going to have slightly different boiling points. Right? We can do something similar with our rings, so our aromatics, so ortho and meta dichlorobenzene. So dichlorobenzene means it's got 2 chlorines, right? So I've got a chlorine here and a chlorine here. We have not covered this yet, but there are names for where you're going to put those. You're always going to put one guy up at the top, right? And then the positions, whether you're down 1, 2, or opposite, those are called ortho, meta, and para. Right, so if it was down here, it'd be para. So ortho, meta, and para, as well as omp. There it is. Right? So in ortho and meta dichlorobenzene, right, similar regions as located by the dashed lines are occupied by different atoms, right? So this chlorine is next across from this hydrogen, right? That's different. This chlorine and this hydrogen, this chlorine and this hydrogen, different. In our para dichlorobenzene, my chlorines are now located opposite each other. Hydrogens are located opposite each other, and those hydrogens are located opposite each other. And so that one is going to be nonpolar. Right? So drawing molecules to show their dimensionality in 3 dimensions on 2D paper is a little tricky. Right? So how are you going to represent things without having to use shading or fancy graph paper to indicate it? Like, what do you do if you're a lowly chemist and not some sort of Michelangelo, right? So how do you draw these 3D representations on a flat plane? By convention, we're going to put the central atom in the plane of the paper, and we're going to put as many other atoms as possible into that same plane to make our lives easier. And then we're going to indicate whether or not they're going to come out of the plane of the paper towards us using a wedge, or for atoms that are going beneath the plane, we're going to use a hashed wedge. Now, sometimes you will see people kind of mixing those. They might do a dashed line without making it a wedge. Sometimes you might see a dashed wedge like this, right, where that's going away. It's a little bit flexible. Sometimes you'll see this as a boulder line, right? So you might see like carbon, and then we'll put one hydrogen here, and then another hydrogen here, and one of them will be coming out, and we'll do it as a bold line, and then dash, 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 going away. Okay? So let's look at some examples. In a linear molecule, all 3 things are going to be in the same plane. Right? So A and the 2 x's are in the same plane. Same thing with our trigonal planar. Same thing with our bent molecule. We can get all of those into the same plane. In our tetrahedral geometry, we're going to lock 2 things into the plane of the paper. Right? One will be coming out towards us. That's this dude. And one will be going away from us. And the same thing with trigonal pyramidal or the trigonal bipyramidal. With trigonal bipyramidal, we're going to get 3 things in our plane, and one comes up at us and one thing comes down away from us. We could draw that tetrahedral structure and rotate it so that we've got 2 coming out of the plane at us. All right, so those guys are coming towards us. Draw those big H's. All right, and then we could draw two that are going away from us. All right, so sometimes you might need to do that depending on what your particular molecule looks like and where it is and how complex it is. All right. Our seesaw shape will have three that are in plane. One comes up, one goes out. Octahedral kind of does this nonsense, right, but it's going to lock those into plane. You could also do this octahedral one like this, where you've got your central guy. All right, you got your axis in the plane, and then you can actually keep one of these equatorials on the left, one of these equatorials on the right, and then kind of do, this guy comes out at you, and then this guy goes away from you. You got some variability. Square planar, because it's a plane, sticks in the plane. All right. If you've got multiple atoms and you're trying to represent that, lots of these are going to have larger structures with interior atoms. You just think of them as multiple central atoms. For each multiple center atoms, each center atom is going to have its own designated shape. So, for example, glycine, if you look at the ball and stick model for that, the nitrogen around here, it's got a lone pair. Right, it's going to be trigonal pyramidal. This carbon is going to be tetrahedral, 1, 2, 3, 4 things around it, tetrahedral. This carbon over here has 1, 2, 3 things around it. It'll be trigonal planar. This oxygen over here is going to have 2 lone pairs. So it's going to have a tetrahedral electron domain geometry, but a bent molecular geometry.